totally fine. So I built this. I built this to compare and contrast the proportion and the mean. And I said, I'll have this PowerPoint up for you guys too a little bit later. So you don't have to write all this down if you don't want to. I don't have the videos up. So this is what we did with proportion. When you have an unknown population parameter, little p, you get the center, p hat, and you build the margin of error around that, center of the spread, and then you apply that guy like that. Everybody's okay with that? That's what we're doing for the past couple days together. Let's do something similar for averages, okay? And you're already halfway there. You're already halfway there. Here it comes. Here it comes. We're going to estimate the average, which means we don't know what mu is. That means we're going to go with x bar for our center. We're okay with that. You guys are okay with that as well. Now, this guy, there's your S. Yes? What the hell? Where'd that come from? Root n. Does that ring a bell from central limit theorem? Vaguely. This, in my opinion, is the most surprising result of the central limit theorem. That the standard error in the central limit theorem shrinks as a function of the square root of the sample size. That's why I use those weird numbers in 243. 4, 9, 16, 25, 100. Why did I use those? Because they're weird? No, because they're perfect squares. Because root 4 is 2, root 9 is 3, root 16 was 4. I use those to get nice numbers out. And then, over here, if you ignore the multiplier, that's just the standard error, S over root n. What the hell is that? T. It looks like it's in the same place Z was. So it's like a multiplier. It's a multiplier for how confident do you want to be. But why is it called T? Don't worry for that right now. We'll get to that in a moment. Just a moment. Literally a moment. But I want you to see what you're going to be building at the end of the day. You don't know where mu is, but you know with a set level of confidence, he's going to be between a margin of error down from x bar and a margin of error up from x bar. Do you see how that's the same as this with different statistics? So all this probably makes sense, at least with a pot of strong coffee, except for that. Why would I call that T? Why not just call it Z? Why not just call it Z? Because Z is what we're used to, right? We're used to the Z distribution. Z equals 2, 95% confidence. Z equals 1, 68% confidence. Z equals 6, ridiculous levels of confidence. Well, I want to tell you about why it's T. But I want you to read this first. Have you ever seen the movie The Commitments? One of the funniest movies ever, in my opinion, ever made. That last line I put from The Commitments. So, 1899, the tiny Guinness brewery needed some quality control. At the time, Guinness was not as worldwide known as it is now. It literally was in Dublin, and pretty much people that were directly around Guinness got Guinness. So, they put a call out to arms. Maybe it looked like this, I don't know. This was my own imagination. Maybe it looks something like this. Let's go hire a statistician to help us out. But it's amazing how you might not realize that Guinness actually did have a chunk in what you're sitting here learning right now. This gentleman here, William Gossett, is the gentleman that worked for Guinness. He answered the call in 1899. He answered the call. The problem was, he had to be quality control for Guinness. He had a lot of jobs, but one of them was basically consistency testing and also crop yield testing for the different kinds of grains they used. The problem was, well, there's a couple problems. Number one, Guinness was exceptionally small at that time. So, you know how we talk about sample sizes being large enough? They didn't have that luxury of large samples. They had tiny samples. So all these bell curve things we keep talking about being, let's just assume a bell curve. He couldn't always do that. He couldn't always assume a bell curve because he wasn't meeting the requirements for a bell curve. He wasn't saying, oh, I got four plants that germinated. We're making a 6-pack this month. But he had to do statistics on those 4 plants. So his first thought was, okay, I got small samples. How about my taste test, my quality controlling? Well, how much beer can you drink until you can't think anymore? So can I get enough done with a small sample of taste testing? So he had all these wonderful challenges he had to deal with right? Staying sober and staying accurate while dealing with exceptionally small samples. Exceptionally small samples. So what he did was, he made up his own distribution. But this sounds kind of strange, right? Made up his own distribution. And I thought it was insane when I first heard it. Like, you can't just make up a distribution. Then I read more, I'm like, son of a bitch. He didn't just pull it out of his hat. He developed it using Monte Carlo methods. Check this out, it's totally badass. He called it the student T distribution. That T that was in that margin of error calculation is a nod to that. Why did he call it the T distribution? His last name is G. Why didn't he call it the G distribution? Because Guinness had a policy that you couldn't publish on the company's dime. So he made up a letter that had nothing to do with his name at all and published it under that. And we're stuck with it, unfortunately. All we know now is occasionally that William Gossett gave it to us. Yeah, it's okay.
For taster.
For taster. Beautiful. I don't know why he called it student's tea, but yeah, for taster. Tea for taster. Now, this was his, I think this is elegant. His elegant solution was, well, I got a small sample. The central limit theorem kind of guarantees that I can target the average, but because my sample's so small, the standard deviation is going to be off the charts huge. He also realized that with larger samples, the variation is going to shrink. But he created a distribution he created that equation by pulling paper out of a hat and looking at his results. He inspired me. You're going to do something similar, not with paper and hats. At the end of the course, you're going to analyze a CPR exam, multiple choice CPR exam, using Excel to pull paper out of a hat. He inspired me to build my own distribution. I call it the C distribution because I was listening to The Clash when I was coming up with it. So we're going to come up, it's amazing. You can build your own distributions. They're wonderful. They're wonderful. So this was his solution. He's like, let's create a new solution that allows for small samples and the increased variability of the small samples and the increased variability. So what I wanted to do now, oops, I'm just going to plug that. The curve will not be like the bell curve in that it won't always look exactly the same. Let me see if I can show you what I'm talking. Whoops, that's quite all right. I'm going to get it old school. School things, Matthew 44 lessons, single me. Oh, it's already open down here. Here it is. All right. So what I've done here is I've built your normal curve, your bell curve, your standard